Okay, now I'm starting the class. So today is live session 8 of the course Geographical Information System. Last time I have covered, am I audible to you?
Yes, ma'am.
Okay. Last time I have covered the creating and maintenance of database and the spatial query and how it has been established, what are the things associated with that, database design, spatial analysis can be done over this database management system, and how the editing tools in GIS is working with the basic editing of geometry also I have covered in the last class. So today's class will be on what is remote sensing, what is electromagnetic radiation, what are the principles associated with remote sensing, what are the active and passive remote sensing, basic resolutions, type of resolution, the advanced and basic spatial analysis can be done in GIS, how it is, and the GIS models, and the DEM, tin, and contour, what are those things, and the data limitation uses in GIS. So today's class will be based upon how the remote sensing will play a role in GIS, what are the things should be taken care, what are the basic idea of the remote sensing in application in GIS. So let's introduce here I am introducing the remote sensing. So remote sensing is the measurement or acquisition of the information of some property of an object or phenomena by a recording device. Means we are not going in and touching or being in contact with the object. We are remotely sensing the information without being in contact or intimation with the object or the phenomena under the study. So, like that, here you can see the imagery. The satellite is going to capture the imagery remotely without in contact with the object, and they are getting the information of the particular object. How the remote sensing data are the key technology for updating many type of GIS data. About 75 to 85% of spatial data layers have been derived from analysis of aerial photographs and the satellite data from the remote sensing. So first we should know what is the remote sensing. RS, now onwards I will pronunciate RS, which means remote sensing. It is teledetection, means earth observation from far through satellite. So remote sensing is more than looking at the picture, because the sensors or the satellites giving you a photograph or picture imagery. So it is a different way of looking consciously at the earth surface or the objects or the features with prior knowledge, means you're knowing what you're going to sense. So remote sensing, observing with artificial eyes. What are your artificial eyes? Are these sensors. So remote sensing includes all methods and the techniques used to gain qualitative and quantitative information about distant object, means where you can't reach distant objects without coming into direct contact with these objects. So look, no touch. It means you can look on the object or the feature of the earth surface, but you are not allowed to touch. Okay, you are not being in contact with. This is the remote sensing. So why we are doing remote sensing? You might have some basic questions in your, like, how much of what is where. Have you understood? Means, like, if you are sensing any urbanization, or if you are sensing the flood inundation, or if you are sensing any disease spread, so without being in contact with the community or the things, how much, what is, and where, what is the shape, what is the extent, how large or how small it is, the area, the boundary, the lineament, has it changed? We can access the change also with the time period. Let me see, someone is yeah. So how much it has been changed, like how much the population density has been increased, how much the rainfall occurred and it caused the flood nearby the river basin or something. So what is the mix of the object? Means if you see the rural area going to convert into industrialization or urbanization, so what are the mix object will be coming into picture? What are the industries are establishing? Where haphazard development is happening? So these are things can be sensed through remote sensing methods. So these are the basic question when we go for remotely sense product. Now, remote sensing application generally have been done for mapping. Means you want some inference, some maps from the particular analysis, or you monitor the things. Okay, you are monitoring the urbanization, you are monitoring how the behavior of the water or rainfall occurred. Is there been a drought situation or the flood situation? How the modelings are going to affect, so we will model such kind of thing. Means it can be worked on globally, continental, landscape, or locally also through your regional study area, or it can be for a particular landscape. Means you are interested in only for river basin studies, so you will select a watershed area. Or you are interested in land use land cover mapping, so you will select a landscape over which different features are there, land features are there. Or you want to interested in our Indian continent, or globally you want to see the change. So remote sensing help, because as I have shown you how the satellite works, it is allocated at a far distance over the earth surface, and it is sensing all over the earth features, the satellites, and we are getting this imagery or the pictures, and we are understanding what are the features are there temporally and spatially also. So I will tell you about the other types of remote sensing. So as you can see here, as I have told, satellite data can be taken here. There is multi-stage remote sensing. Means people can do ground-based observation also. As you can see here, the crane, how the man is on the crane, and it is showing the landscape. And when we see the airplane or aircraft also helpful to take aerial picture or imagery, high altitude data also up to a certain distance or elevation from the earth surface. So the satellite is the like very far in kilometers far to sense the earth feature. So these are the multi-stage remote sensing products. So why we are doing, why we are assessing the information from remote sensing? Because we are integrating this. We want to know the relationship between the remote sensing and geographical information system. The remote sensing system contributes database for GIS. Remote sensing provide timely and low cost data to the GIS, because when you want to collect a large scale data, you can't go individually as taking your own team and go to do survey on each of the places and collect. Sometimes we are not in need of detailed information, but if you want, there are some satellites which will help you to get the detailed information regarding a particular earth feature also. But for large data sets in low cost, you are able to get through remote sensing products. I will show you some imagery of different remote sensing products also in the slides, for the slides. The third point saying is remote sensing data formats like raster is compatible. As I told you, the different difference between the raster and vector data. I have told you how the raster data is helpful as compared to vector data. When we have very big amount of large amount of data sets, it will be easy to work with raster format. And I will show you how the raster and pixel will work when we want to access the earth feature, and we want to discriminate between some landscape features, and we want to get some inference through spatially and temporally, or different bands, spectral bands also. So remote sensing and GIS use similar equipment for analysis and display. So these are the same thing. We are getting the data, we are collecting the information through remote sensing sensors, and we are implementing it into our geographical information system tools. Okay, so these are the relationship between remote sensing and GIS. So let's see what are the stages in remote sensing. As I have told, RS here is speaking remote sensing. So if you see here how the sensors, you please see my cursor. Wait, I will show you. Okay, how the sensor is sensing. This is the satellite, this is the source. Sun is the source of our electromagnetic radiation. The sun is radiating the light to the earth's surface feature like plants, trees, water bodies, bare soil, paved road, the buildings, the industries. And what it is giving, it is reflecting those light through the atmosphere, and this satellite is sensing this reflected light. And this this satellite products or this imagery we are going to process in our system, and we are getting some analysis, distribute for analysis. So the stages in remote sensing is: first, the emission of electromagnetic radiation, EMR. I will call it electromagnetic radiation as EMR, which is sun or self emission. Sometimes we will allocate, we will throw our own light from the sensor and we will collect the information. Sometimes we are using sun's radiation and we are collecting the earth surface feature reflectance. So the transmission, first stage is emission of this EMR, electromagnetic radiation. The second stage is the transmission of the energy from the source of to the earth surface features, as well as absorption and scattering. So what is happening when EMR is reflecting on the earth surface? Some energy is going to be transmitted from the different feature of the earth surface. Some are getting absorbed and some are getting scattered. I will tell you about this stages also further in detailed way. Interaction of EMR through the earth surface feature like reflection and emission. The fourth stage is transmission of energy from the surface to the remote sensor. What is happening? The transmitted or reflected these radiations are going to the remote sensors, the satellite, and the sensor data gives the output as an imagery or reflectance, and the data is going to be transmitted through our transmitter, and we are getting in our processor or the systems, and then we are analyzing. So these are the six stages in the remote sensing which are going to happen when the electromagnetic radiation interacts with the earth surface feature. So the remote sensing basic processes are: data acquisition, means energy propagation or the platforms, the processing, the conversion of these energy patterns to the image which is happening into our system, and then analyzing, qualitative or quantitative analysis based upon the earth feature data sets, and then the accuracy assessment, radiometric or geometric correction, because the atmosphere having different layers, as I told you, the troposphere, stratosphere, mesosphere. So different layers are causing some interferences. To reduce these errors through the atmosphere, we are we are using some accuracy assessment while correcting this radiometrically and geometrically. So these are some more remote sensing data processing terms. And then information distribution as a hard copy or CD or ROM or byte. So we will process, then we will get the information and we will distribute to the decision makers. So this is the basic processing into the GIS of this remote sensing data. So this are another flow charts, like remote sensing data like air photo, digital data like what we are collecting from our sensors. These are the data product. Then visual or digital interpretation we are doing, like sometimes we are able to sense through seeing the image itself. Our eyes we are able to understand using some understanding the wavelength of the spectral signature. I will tell you what is are the spectral signature. So few visual few image interpretation can be done by our eyes itself, or few we needs digital, because our eyes are not able to assess the information more than or less than our visible spectrum. I will tell you what are the EMR, electromagnetic spectrum, what are the visible spectrum, which we can see through our naked eyes, or ultraviolet or infrared, which we are not able to access. So we will do digital interpretation of the remote sensing product. Then we will go to statistical analysis the information products like GIS datasets, map and statistics. And then further it is going to the users and decision maker for the target audience. Okay, these things are here is like urbanization is haphazard, so here we can think of, or these are the barren lands where we can establish some more industries which land are not sustainable for agriculture production, or these are the uh, like you can say if you think about some disease spread or something, so these are the prone area for the disease, like that, or these are the very dense population area, so like that we can make some inferences. So these are the last stage of the remote sensing process. So in a detailed manner, two important activities are coming in remote sensing. First is data acquisition and second is data interpretation. Generally the remote sensing satellites, it will do, it will gives you the data from the electromagnetic radiation. It can be active sensor, it can be a passive sensor. And what further our, as a as a GIS specialist, what are our functionality is to interpret the data visually or digitally, and then give some inferences to the general or decision makers. So the electromagnetic radiation is the chief information carrier from the object to the sensor on board space or airboard, like space or air based platforms of the three basic like wavelength, frequency and velocity characteristics, because every earth feature having different wavelength, different velocity and frequency of electromagnetic radiation reflectance. Then EMR wavelengths is important from the point of view of remote sensing. That's why we are more focused towards the wavelength of each feature. I will tell you when I show you the spectral signature of vegetation, bare soil, water body. So it will behaves in different manners. And then data analysis have been done like data processing, compilation and application. That are the further steps in remote sensing data processing. So let me tell you about the passive remote sensing and active remote sensing. So when we just take the from the electromagnetic radiation of the sun itself, we are getting the reflected radiations. Means we need not to throw the lights from the sensor and we will collect the information. If you see here, the this image is telling you the passive reflected solar radiation. Means here what is happening from the sun's radiation itself, the reflected lights are radiations are getting captured in our sensor, and we are assessing this reflected information from the sensor using the radiation emitted by the object. So this is called the passive remote sensing. And then when we our sensor s- is scattering our sensor is throwing the lights on the surface and earth surface and collecting the information of the reflected radiation also, then it is called active remote sensing. Sometimes it comes under microwave remote sensing. Sometimes we are not able to capture the detailed reflectance from the earth feature, then we need the active remote sensing. Means we need to throw in lidar or radar, we need to throw the lights from the sensor itself to get the reflectance from the earth surface feature. That is called active remote sensing. Guys, are you getting? If you have any question, please ask me. I will answer in between, no problem. Hello? Okay. If you get any doubt, please let me know. I'll continue. So the active or passive remote sensors, if you see here also how the sun is radiating the electromagnetic radiation and sensors are capturing the reflected radiation. So when we call passive sensors measure the amount of energy reflected from the earth's surface. Passive remote sensing system records the energy that naturally radiates or reflect from the object. When it comes to active remote sensing, you see here how the radar imaging is reflecting emitting the electromagnetic radiation from the sensors and taking the reflected radiation from the object or the feature of the earth's surface. The active sensor emits the radiation in the direction of the target. It then detect the measures the radiation that is reflected or back scattered from the target. The active or microwave remote sensing system supplies their own source of energy. As I told, it is emitting their own source of energy to get the reflectance from the earth surface feature, directing it at the object in order to measure the returned energy. Okay, so we are interested to sense the reflected energy. So when it comes from the natural or the sun electromagnetic radiation, we are calling is it as passive remote sensing. But when we are allocating emitting the radiation are emitted by the sensor itself, and the reflected are going to capture to the sensor, then it's called as active remote sensing. Generally it comes under the microwave region. So, what is electromagnetic radiation? As Sir has discussed in the class lecture itself, the when the when the it is the perpendicular electrical and magnetic variation. You see here the light, the velocity of light direction, and the electromagnetic wavelength. So, the trough and the crest, the distance between two troughs and the crest is called wavelength. Okay, so the electromagnetic is spectrum is the energy available from the sun is described by electromagnetic spectrum, which is energy source. If you see here, the here the wavelength is given from 300 meters, 300 nanometers to 0.003 nanometers. Here you can see when the wavelength is large, so the energy is high, and the wavelength is low, the energy is low, as Sir taught in the class. So please focus on this figure of the electromagnetic spectrum. Here we can see the frequency or the wavelength in nanometers. For the visible length, it is lying from 400 nanometers to 700 nanometers, like Vibgyor, violet, blue, green, yellow, orange, red, which we are able to visualize from our naked eyes, is the visible light range, that is from 400 nanometer to 700 nanometer. And if you see here, just before this visible range, this is ultraviolet, x-ray and gamma ray. And after this visible, when red is about to finish, here the infrared, microwave and radio wave regions are there. So these are the wavelengths given here in nanometers. Okay. So the concept of electromagnetic radiation and the principle behind this is energy source and radiation principle, based upon the Stephen Boltzmann law, Wayne's law, Planck's law. So these are the different laws in electromagnetic radiation which you should know. The different sensor measure different part of electromagnetic spectrum. So we are having some division of electromagnetic spectrum. What are those? X-ray, UV, ultraviolet, visible range, infrared, microwave and TV. So these are the TV means radio waves. Okay. So this is the general division in the electromagnetic spectrum. So where the visible region is lying, where we can see this visible region, that is lies between ultraviolet and infrared. If you see, just before visible there is ultraviolet, and just after visible there is infrared range. So in general, we are more interested in visible range because we can visually analyze or interpret any image from the remote sensing sensors which we are getting in a proper manner into this visible region spectrum. So ultraviolet having the wavelength of 0.01 to 0.38 micrometer, and when micrometer means 10 to the power minus 6 meter. Okay. And when it comes to visible region, means this point 0.4, as I told, point 0.4 to point 0.7, it is nearby to 0.38 micrometer to 0.76 micrometer. For the different spectrums, there are different ranges of wavelength. Similarly, for near infrared, short wave infrared, middle wavelength infrared, long wavelength, and far infrared. So like that, there are some division in between the spectrums itself. So for a particular range of the wavelength and the microwave. So we are more focused towards the visible range to get the earth feature visually, to interpret it the remote sensing imagery visually. So let me tell you about each of this division of the spectrum. The ultraviolet, which is zero point 0.4 micrometer, if I say just before this visible range, you can see here not much is done with the ultraviolet for remote sensing, since these are the shorter wavelength. As I told, these are the longer wavelength and these are the shorter wavelength. So easily scattered by the atmosphere. So it can't capture more radiation, or it can't, so it is scattered, so it is not in use in terms of remote sensing. So when we talk about visible range, visible radiation spectrum, generally we will deal with blue, green and red. So the blue lies from zero point 0.4 to zero point 0.5 micrometer. Micrometer, as I told, 10 to the power minus 6 meters, or if I speaks in nanometer, it will be 400 to 700 nanometer. It means 10 to the power minus 9. Okay, so visible region of the electromagnetic spectrum falls between the infrared and ultraviolet range, which is from zero point 0.4 to zero point 0.7 micrometer of the wavelength. Okay, here you can see also the infrared radiation lies from zero point 0.72 to 15 micrometer. If you see here, this is the infrared region: near infrared, mid infrared, and thermal infrared. There are subcategory of infrared region, as I showed you also. The near infrared reflect can record on film. It also reflected can be detected using electro optical sensor, means more good sensor it can be reflect, or it can be sensed. The thermal takes the emitted radiation, can only be detected using the electro optical sensor. For this also we need electro optical sensor to sense this emitted radiation. Now the microwave radiation sensed by the radar sensor, which comes under which one? Can you tell? Just now I told, right? The microwave radiation comes under, okay. The microwave radiation comes under active remote sensing. Okay. So this is having the wavelength of 1 mm to 1 meter. So in general, what energy or quantum is? The energy of quantum in terms of joules is the directly proportional to the frequency, that is the Planck's law. It is when the proportionality sign is going, there is a constant coming h is called the Planck's constant, which is which value is around 6.626 into 10 to the power minus 34 joule second, and the frequency f is the frequency, so the energy is proportional to the frequency. But we know the frequency is the inversely proportional to the wavelength. That's why the energy is inversely proportional to the wavelength. As sir taught in the class also, as we know, q is directly proportional to the wavelength, frequency, and the frequency is inversely proportional to the lambda wavelength. So it means q is, sorry, q is inversely proportional to the lambda, means wavelength. It means if the energy, if wavelength is less, energy will be more. Okay, so energy is inversely proportional to the wavelength. Are you getting, guys? Malay? Okay, let me continue. Then few more concepts are there through this energy and the laws is Stephen Boltzmann laws and Wend's displacement law. What a Stephen Boltzmann laws is telling is the equation describes the total amount of radiation emitted by a body, black body, as a function of its temperature. It means the energy is m, here is the energy watts per meter square. Watt per meter square. M is, sorry, okay, m is directly proportional to the temperature power of 4. So we can say here m is directly proportional to the T to the power 4. T is the absolute temperature in Kelvin. So and sigma is when this proportionality sign is changing to equals to it, there is a constant coming which is called Stephen Boltzmann constant. So the and here Stephen, as per the Stephen Boltzmann equation, the total radiation emitted by the object is directly proportional to the surface temperature. It means when temperature increased, the energy radiation also increased. And when we speaks about Wind's displacement law, it tells the wavelength is is inversely proportional to the temperature. It means if the temperature is high, wavelength is low, and when the wavelength is low, the energy will be, energy and wavelength having the inverse relation, no? So when the wavelength is low, energy will be high. Okay, it will be more. Okay, so here it showed the how with the wavelength and the spectrum of radiant excitance is changing. So here as per the Vane's law, there is a graph plotted between the radiance excitance and the wavelength on the x-axis. So you can see here. So for sun and earth surface, which range it is lying. So it is telling here, it's shown here. Okay. So the object EMR interaction means through the electromagnetic radiation, the earth surface interaction, how it behaves. The EMR can be scattered, reflected, or absorbed. When this electromagnetic radiation interacting to the earth surface, there are four processes can happen. It means it can be scattered, it can be reflected, or it can be absorbed, or it can be transmitted by the object of the earth surface. So scattering can happen in two ways: selective scattering or non-selective scattering. In selective, we are having one is relay, another is Mie scattering. I will tell you what are these things. So these are the wavelength of this selective and Mie scattering, and the approximate dependency on the particle size. This behaves on the atmospheric particle size. So the kind of particle means when Rayleigh scattering is happening when there is air molecule, or Mie scattering happening when the wavelength and the particle dia lies between zero point 0.1 to 10 micron meter, which is having generally smoke and haze particle into the atmosphere, and non-selective scattering happening more than 10 micron meter particle size, and this is for the dust and fog or clouds. When the particle size is very large, then it is coming under non-selective scattering, and when it is very low or in this range, it is coming under selective scattering of Rayleigh and Mie. I will show you one of the example of this scatterings also. So you know why the sun appears, why this sky appears blue in the daytime. So Rayleigh scattering, why the sky is blue, means when the rays from the sun coming through the earth's surface through the atmosphere, what is happening? Spherical scattering of rays in the blue part of the spectrum. So mostly the other radiations like red or blue, The atmosphere scatters the blue light more effectively than other red or green or any other light. So hence mostly we can see the sky appears blue in daytime because sun is at the pole, at the directly towards the earth surface. So in the daytime we can see sky appears as a blue. Hence the mostly blue light reaches your eyes when you look at the sky. You can see here how the electromagnetic radiation coming from the sun to the earth surface, and it is scattering. Due to scattering, it is called Rayleigh scattering. It comes under the Rayleigh scattering. Other lights or other bands of spectrum are getting back only the blue color is visible to our eyes. That's why in daytime we can see sky looks blue, and the evening time when suns reach to the horizon, so it more more blue are getting scattered, and we can only see the red light reaching to the earth surface. Here we can see the atmosphere scattered blue light more effectively than the red light. Hence mostly red light reaches your eyes when you look through the thick through a thick slice of the atmosphere at the setting sun. Setting sun means when sun is in the evening, so it looks red color. Okay, so this is the two, like generally we can see in daily life, two examples I have given for scattering. This is a Rayleigh scattering example. So if someone asks you regarding why sky appears blue in daytime, so you can tell the answer, and why sky appears red in the evening time, you can tell the answer. Okay, so what more we can see when the energy matter interaction happen from the electromagnetic radiation. The science of the remote sensing detects and record this interaction or the changes. The resulting data image is or are interpreted to identify the characteristics of the matter that produced those changes. It means, see what is happening here. When the electromagnetic radiation incidenting on the earth surface, some radiations are getting scattered, some got emitted. You see here, I will show you. See, these are the emitted radiation, these are the scattered radiation, and some are getting reflected back to the sensor, and some are getting transmitted or refracted, you can say, or some are absorbed by the earth surface feature. So this phenomena used to happen when EMR interacts through the earth surface feature. Then what more, the responses of the feature on the earth to electromagnetic reflectance, electromagnetic energy happens like reflection, transmission and absorption. Okay, so for the same incident wavelength of radiation, what is happening here, if you see, this equation is telling you the incident wavelength, the transmitted, reflected and absorbed. This equation is telling you about this. You understood the spectral reflectance or the spectral response of the spectral signature. So what is happening, this is the reflection, this is the absorption, this is the transmission. So the total radiation coming to from the sun or the electromagnetic radiation is the sum of the reflection, transmission and absorption. That is totally will call as 100% radiation. Okay, total spectral reflectance. So if you see the processes of atmospheric radiation, see, some are transmitted, when absorbed and emitted and scattered by the aerosols or molecule. Here you see this image is telling you about this image. If you look here, emitted, transmitted, reflected. What happened? Someone is asking something. Okay, so emitted, transmitted, what is happening? This is emitting, this radiation, the transmitted, the absorbed or scattered, and this is reflected. So here you can see when the electromagnetic radiation is coming or interacting to the earth surface feature through the land surface, through the water body or the ocean, it is some is getting emitted, some is getting reflected, some is getting transmitted or absorbed through the ocean to the land surface, like this. So you can see here. I hope I'm clear with this. What are the phenomena happening when the EMR is interacting to the earth surface feature? Now what is the spectral signature when this incident is happening? The EMR is incidenting to the earth surface feature. How the different feature on the earth surface behaves or reflect the radiation, and what it is giving, it's called as spectral signature, a set of measurement values for the reflectance or the radiance of the earth object, each value corresponding to a specific well defined wavelength interval. So each value having the different reflectance in a different wavelength intervals. So the reflectance characteristics of the earth surface feature may be quantified by measuring the portion of incident energy that is reflected. Okay, so the reflectance characteristics of earth surface feature, this is very important line guys, may be quantified by measuring the portion of incident energy that is reflected. So spectral reflectance is the ratio of reflected energy to the incident energy as a function of wavelength. So the spectral reflectance is the, in terms of mathematical equation you can say, the ER, energy reflected for the particular wavelength, divided by the energy incident EI for the as the function of wavelength into 100. It comes in a 0 to 100%. So like that it it works. So how there is a typical spectral reflectance curves for the for the earth surface feature like vegetation, soil and water body. So you can see here how the reflectance for the water body. So for water body, generally water body absorbs the electromagnetic radiation, that's why it did not show you more reflectance. So here you can see there is a reflectance around 2 1 or 2% for the clean water body. When it is like polluted or something, so it will show some more reflectance I guess, because it is not pure, so it is not appear as a pure water body. For the vegetation, if you see, as we know, our visible spectrum is in the range of zero point 0.4 to zero point 0.7. It means until here, okay, until this point. Okay, so if you see, water body is somewhat absorbing, it's not reflecting more. So that's why reflectance is very low for water body, clean water body. But if we see here for the vegetation in the visible spectrum, this is the visible, visible, visible spectrum, which is zero point 0.4 to zero point 0.7 micrometer. So in this range, if you see, the vegetation did not show you more reflectance. But when we go to NIR, because after this visible spectrum, what is there? That is near infrared, infrared range. Shortwave infrared, near infrared, as I told you, different subset of infrared also, so it comes under infrared range. So we generally see the reflectance of vegetation is more or clearly differentiable in near infrared range. That's why this band show more clear vegetation features. And when it is, so you can see the reflectance for the vegetation in this range is around, you can see, around 40-50 it is lying. And for, okay, and for, if you see this bare soil, it is this brown color one, spectral signature. You can see it means in visible range it also did not show more. When we go for after this NIR band, then we can see this bare soil or such feature, gray brown features and all. So this is the typical curve of spectral signature of these three features: vegetation, soil, and water body. So, the selective transmission of electromagnetic radiation by the Earth's atmosphere is generally we will follow this atmospheric window. The atmospheric window defines the wavelength range in which the atmosphere is particularly transmissive of energy. Means what is happening? See, some aerosol particles, some ozone, some water vapor is not allowing the reflect reflected lights to come back to the sensor, or sometimes it got scattered in between the atmosphere interferences itself. That's why we are having a atmospheric window where we we are able to detect the reflected radiation. The visible region of electromagnetic spectrum resides within the atmospheric window. This is the very important line, guys. So please, please mark it. The visible region of electromagnetic spectrum resides within an atmospheric window. That's why it is important. The atmospheric window is about zero point 0.3 to zero point 0.9 micrometer. You can see here it is, see here it is zero point 0.3 to zero point 0.9 micrometer of wavelength. The emitted energy from the earth's surface is sensed through window of 3 micrometer to 5 micrometer and 8 to 14 micrometer. Okay, the radar and passive microwave system operates through the window region of 1 mm to 1 meter, as I told you about this microwave band itself. So the transmission through the atmosphere is very selective, very high for wavelength for zero point 0.3 to zero point 0.9 or around 1 micrometer and more than 1 centimeter. Moderately good for 1 to 20 micrometer or zero point 0.1 to 1 centimeter, and very poor for zero point 0.3 micrometer and 20 to 100 micrometer. This defines the atmospheric window. So we can sense the imagery in the particular atmospheric window. Okay, so this is our visible spectra. You can see here. So we are more interested in visible spectra because our eyes can sense or see this feature clearly. Okay. So what are the application, field of application of remote sensing? As I have talked about what is the remote sensing, the principle behind that, the energy, the spectrum, wavelength, and what are the different energy spectrum of electromagnetic radiation, how the electromagnetic spectrum interaction through the earth surface feature also. So there are number of application, field of application in terms of remote sensing products, in terms of meteorology, hydrology, soil science, biology, or nature conservation, forestry, environment studies, agriculture engineering, physical planning, or land surveys. So different kind of remote sensing studies or products have been used for different purposes. Okay, so I will show you some imagery, some satellite imagery which deals with such applications. So generally we have multispectral imagery which is having green, red, near infrared, and blue bands. So this kind of imagery is called as multispectral, which is having different band into a single image, in a single image. So and there are some more satellite vehicles which are getting this resolution, getting this imagery for the given resolution. Like if you see Landsat is giving around 30 meter to 60 meter resolution. Indian remote sensing series data also giving the resolution around 15 to 30 meter only. The spot is giving resolution of around 10 meters to 20 meter, but Iconos is giving very good resolution. These 4 meter, 1 meter, or these all bracket things are the resolution. Speaking about the resolution of image, I will tell you This is a spatial resolution, and these are the bands are spectral. That's why it's called multispectral bands. Okay, because it is having different color bands into a imagery, and the QuickBird is giving you the resolution of about zero point 0.6 meter. I will show you this all imagery so that you will find some more interest into understanding this satellite image. So if you see here, the satellite remote sensing of the earth as land ocean chlorophyll analysis for the September 1997 to the present, how it is sensing the satellite, and the satellite view of the earth in night, so how it looks. So see, you should know the natural color composite. Natural color composite meaning is what we are seeing in visible spectrum, which is red, green, and blue RGB, which generally our naked eyes will appear. So if you see the Google satellite, some imagery, as I have showed you also in our previous classes, you can see this vegetation in green color, this land in general color of brown, and something general natural color composite. Okay, when we convert some band of color into another band, because we are having multispectral band which is having different band for a different satellite or different imagery, we are having different band for the different color spectrum. So when we are interested in vegetation, as I told you in spectral signature, how vegetation behaves or reflects a very good signature when we see in near infrared. So in terms of Landsat, the near infrared band is fourth band. So that's why now it is NIR, R means, and G band means second band is green band, third band is red band, fourth band is near infrared band. So what are the vegetations? If you see in this natural color composite, what are the vegetations were there? They all are coming into shades of red, which is near infrared. And the other features which are earlier showing the ground surface, now it is in green color. So we can easily differentiate the vegetation of different shades of red color or near infrared color. So this will called as a false color composite when we are changing the band from natural to any other bands. So this is the Landsat 30-meter resolution for mountain of this St. Helens or St. Adams. So Columbia River. And this is the Indian remote sensing class 1C list 3D imagery. You can see how it appears. Satellite image. This is Iconos image. As I told you, see, Iconos resolution is around 4 meter to 1 meter. For multispectral it is 4 meter, or for panchromatic band, which is only a single band but it is having a good spectral signature. It's a good spectral um, because a single good spatial resolution, so that is 1 meter. This all our numbers are telling about the spatial resolution. I will tell you what is the spatial resolution in detail way my further slides. So Iconos is telling you, see how clearly the features of the earth surface is appearing, because this is the multispectral band, 4 meter resolution band. Okay, then this is the advanced, as I showed you here. Just a minute, guys. So, what I was talking about, this AVHR HRR is advanced very high resolution radiometer of 1 kilometer resolution. The same St. Helens, this Columbia River Olympic pen. You can see here how nicely it is showing. This is a false color composite. As I showed you, the red colors are showing all the vegetations features, and this dark, this light blue color is showing about this urbanized structure. So this is the advanced very high resolution radiometric of NASA imagery. And you can see this is the geostationary operation environment satellite from Indian remote sensing IR-4. So how it is appearing. So this is the Modi's 250-meter resolution image, the land surface. This is the Landsat false color composite. Landsat thematic mapper. Okay. This is the spot 2.5-meter resolution. How clear this natural color composite imagery is. You can see here. This is what Washington, USA. The image is captured on November 2002. So how clearly it is appearing. And then this is quick bird 0.6-meter resolution showing this area. So this is Iconos 4-meter multispectral. This red color. This is also a false color composite multispectral band. And this is Iconos 1-meter resolution panchromatic band. See here how nicely it is showing this all detailed feature. If we see here how nicely it is showing the feature, see all these lines, boundaries are very clearly appearing. This is called panchromatic band. It's having panchromatic band is having one band black and white color of good high spatial resolution. This is the radar, radio detection and ranging imagery of this Gabriel Valley. You can see how nicely it is showing the features of the Earth surface. This is taken in May 26, 1994. This is LIDAR, light detection and ranging imagery. So how this image is the bridge or the island of this taken is 2005. This is the Modi's land reflectance and the sea surface temperature in degrees centigrade over the earth surface, how it is locating the shades of the reflectance. So now, as you understood what is remote sensing, how it behaves, what are the electromagnetic spectrum, so let's come how the remote sensing images were looking and what are the inferences we are going to get from these images. So generally we are having from the remotely sensed data we are having images, or you can say how we say rasters are in image format which are in pixels, the number of pixel, the number of rows and column which is having some dn number, digital number, which these are all digital number you can see here. So the image can be understand through different types of resolution. The ability to record and display the finer detail comes under the image resolution. We are more interested to know for any satellite data what are the different resolution to process it further based upon the correction involved into correction to be done and these things. So the four types of resolutions are spatial resolution, spectral resolution, radiometric resolution, and temporal resolution. So these are the four different resolution. As I have showed the earlier picture also how the 30-meter pixel and 1-meter pixel size spatial resolution. So see here how the spatial resolution for the 30-meter pixel and for the 1-meter pixel. You see here for 1-meter pixel how detailed the boundary, the vegetation, the buildings are appearing, and for the 30-meter pixel how it is appearing very blurry. You are not able to detect the feature clearly. So this is the spatial differences, spatial resolution. And when the temporal resolution Temporal resolution means annually or means time when you are getting the data set. What are the frequency of the data sets? What are the cycles? So observation have been taken. So there are very scar annual detection has been taken. And if you see, there are very random, very frequent data have been taken. That's why it is having good amount of data. And the radiometric resolution means the bit, means how the quality of data. If it is 2-bit imagery, how bad it is appearing, it's not clearly visible. But if it is a 8-bit imagery, how the brightness is varying. If you see, for 2-bit it is vary from 0 to 3 only. It is having four values, means 0, 1, 2 and 3. So brightness value lies from 0 to 3 only. But when we are having 8-bit data imagery, it is varying from 0 to 2 to the power 8. Sorry. It is varying from 0 to, it is varying from 0 to 255, because 2 to the power 8 will be 256. So it will vary from 0 to 255, the brightness value of the imagery. So more clear variation you can see here. This, in this imagery here, it is a bit darker, not clear image. So that radiometric resolution speaks about the data quality. Then the spectral resolution, as your wavelength variation, how narrow sorry, I'm sorry guys, excuse me. So the narrower band and uh, this is the narrow band, means there are four bands. If you see, blue, green, red and near infrared. But here in the band itself there are narrow strips, which is 9 bands, 40 nanometer width. So it means more variation you can see in one image. But here not more variation. So that is called spectral resolution. Bands, number of bands. There is 4 band only, there is 9 band. So this is the spectral resolution. Okay, so in detailed manner, what is spatial resolution? This represents the ability of the sensor to detect and distinguish small object and fine detail. It is dependent on instantaneous field of view of your camera of the satellite. Okay, the instantaneous field of view is the angular cone of the sensor, and it determines the area on the earth's surface which is seen from the given altitude at a particular moment of time. So you can see here, means what is happening. I will just give you a brief how it is telling about this capturing of this spatial resolution. What is, you are having your satellite here, and it is, this is the earth surface. It is, there are some feature, some vegetation, some buildings, okay, some buildings, okay, some industry. So what it's having, any any satellite having a instantaneous field of view, means the area or the covering, uh, the boundary of covering. So when your instantaneous field of view, the angular cone, this is the angular cone of the sensor, and it determines the area on the earth's surface which seen for the given altitude. So from this altitude, this height, what area it is covering, that is the one at a particular moment of time. This is called the spatial resolution. So how clearer the image is. So for the Landsat 30-meter, this looks like this. So a bit blurry, which I showed you earlier. When it's more nearer, so it will be a clear visualization. So like that, there are some examples of different spatial resolution. So here also you can see how 0.5 meter resolution is appearing. Sorry, how this 0.5 meter resolution image is appearing, how this 20 meter resolution image is appearing. The instantaneous field of view means this 1 pixel size, 80 meter by 80 meter. Okay, see here, this is 80 meter by 80 meter. Okay, so this is high versus low spatial resolution I have shown here. This is high one and this is low one. Okay, I hope I'm clear to you. Then what is the spectral resolution? As I showed you, spectral resolution is the number of bands in a particular image. As narrower the band is, as good the spectral resolution. Okay. So this refers the number of band in the spectrum in which the instrument can take the measurement. It refers the number of wavelength band used during the capturing of remote sensing image. The ability of sensor to define fine wavelength interval. As finer the wavelength intervals, as good the spectral resolution. You see here how the this is the nominal spectral resolution of the Landsat. See, and the number of bands. If you see here, blue band, green band, red band, near infrared band, four bands are appearing. So how the image will look like, and when the this is the multispectral sensor. So like that, as finer the band is, as clearer the image, or as clear the earth feature you can visualize through your eyes. Okay. What is the radiometric resolution? When it comes to the quality of data, as I told, if it is 6-bit data range, it will be, see here, 6-bit range will be 0 to 64, means 6-bit means 2 to the power 6. 2 to the power 6 is how much? It is 64. So it means it slices from 0 to 63 of brightness values. So like that, as the range will increase, as nice the variation you can see, as clearer the earth surface feature you can detect. So this is the sensitivity to into small differences in the radiation of an observed object. Ability of the sensor to discriminate very slight difference in energy. The finer the radiometric resolution of the sensor, the more sensitive it is to detecting the small differences in reflected or emitted energy. As I told, the more the range of brightness value, you are able to detect very nicely the earth surface feature in a proper manner. So, what is the temporal resolution? The temporal resolution is the about the frequency of data collection. As I showed you the annual and daily data collection, here you can see the different interval of data collection. So, it refers the frequency of obtaining data over a given area. It is related to the revisit period, because when a satellite is capturing an image over the globe or the earth surface, what is happening? It again, what time or by what frequency it is again coming, means Landsat, sometimes Landsat for the same place, it captures the image in 15 days, or maybe no, around 20 days I guess. You can check different satellite having different speed to collect the information of the earth surface and the cycle period. Okay, for the same place, how how long it is taking to come back to again capture the image of the particular place. So it is related to the revisit period, as I told, which refers to the length of the time it takes for the satellite to complete one entire orbit cycle. As I told, satellites are on the orbits. So for a particular place, when it comes back again, it takes one more cycle to collect the image of the same place. So how long it is taking, it's called the temporal resolution. Depends upon the satellite or the sensor capability, and the swath or the overlap, latitude, and the satellite orbit also. So as I showed, the MODIS is taking 8 days, for revisiting of the same place. Okay, so like that it moves. Now, some more important point based upon your assignment problems I have kept in my slides. So, a digital elevation model, I have told these things in my previous class also, what is DEM, what is DTM, what is TIN. So, I'm giving you the brief for to solve the problem. A digital elevation model is a digital representation of ground surface topography or the terrain. Okay, it speaks about the Earth surface elevation. It is also widely known as digital terrain model. I have showed you one digital DM also. I have downloaded from Bhuvan and imported in my QGIS, and I showed you how the DTM works. So a DEM can be represented as a raster, a grid of a square, as I showed you how the raster resolution is in a grid, in a cells, number of rows and columns, or as a triangular irregular network. It can be as a triangular irregular network. The digital terrain model is used to represent bare earth model without any object heights. The digital terrain model is used to represent bare earth model without any object height. It is not taking care of any artificial or man-made feature like building or any other feature. It is the exact bare earth model or bare earth height from the mean sea level. Okay, so this is the distal terrain model. It represents bare earth model without any object heights. DEM are commonly built using remote sensing techniques, but they may also built from land surveying. It can be built from remote sensing techniques, or it can also be taken care by build this land surveying. Okay, so DEM are used often in geographic information system. Generally, we use DEM for any analysis. It is very helpful. This raster to get the information. It helps in so many parameters of the GIS analysis. That's why it has mentioned here. And are the most common basis of digitally produced relief map. So relief map we can see also, because it tells you about the elevation of the earth surface. So we can get, when we have this TEM, we can get different earth surface feature when we have this DEM. Okay, so please differentiate between, I hope you are clear with this distal terrain model and distal elevation model. Distal terrain only tells you the mean sea level difference to the earth surface, but from the earth surface feature which has been built over that, it did not consider, but DEM consider altogether. That's why it is most oftenly used in GIS. Okay, so what are the characteristics of DEM and tin? So DEM, you can see the image here directly. See, the regular grid based elevation matrix. DEM problems of redundancy will with little variation in terrain. You can see the elevation, the terrain differences. The tin is mosaic of triangular facet, selective sample elevation point. If you see here, tin is elevation points, sample elevation points, gives a sharper image. You see this image and this image, how nicely and sharp or clear differences is appearing in elevation. The model depicts the geographical surface as continuous non-overlapping triangles is called as tin. What is tin? The model depicts the geographical surface as continuous non-overlapping triangles is called as tin. The tin model represents a surface as a set of contiguous non-overlapping non-overlapping triangles. The topographic surface is represented by several triangles. You see here there are several triangles. If you see, you will be able to identify. Wait, I will show you with the pen. See, these are all the triangular network. Sorry, my cursor is not. These are all the triangular network. If you see, they made, now how it is appearing. I hope I'm clear to you guys to show the elevation how through pen I'm not able to make, but I hope you may be clear with these things. Okay, okay. So the topographic surface is represented by several triangles sorry, with each triangle face having an approximate slope or aspect of the earth's surface. You see, having an approximate slope of the earth's surface. See here. You can also see here. So like that it will move. Okay. So few more important points that sir has taught. There are interpolation. These are the spatial techniques, basic spatial techniques which have been taken care in our GIS: interpolation, extrapolation, contour mapping. Okay. So how the interpolation works? Like, interpolation is the process of constructing new data point inside as a discrete set of known data point. When we have known point, if you see here, I have given the example, as we have point A measured, point B measured, but in between we are not knowing what will be the point C. So we have interpolate. This is in between A and B point. But what happens when any point outside of this A and B range we need? This is the point D which is outside. Okay. So we will go for extrapolation. Okay. So this is the extrapolation. So let me describe you through this explanation. The interpolation is the process of constructing new data point inside as discrete set of known data point. It is the process of using point with a known value or the sample point to estimate value at other known points. It can be used to predict unknown value for any geographic point data such as elevation, rainfall, chemical concentration, noise level, and so on. Because if we need any in between point through two or three measured point, so we will follow the interpolation in GIS. Or if somewhere we are not aware of outside the boundary or something, so we will go for extrapolation. It is the process of constructing new data point outside as a discrete set of known data point. Okay, you see this diagram. I hope you I may be clear to you. So this is the interpolation and extrapolation. Okay. So now, contour lines. The contour lines are the lines that connects the location of equal value in the raster data. It can be elevation, uh, it can be uh, distal surface uh, elevation profile. Okay, so raster data that represent continuous phenomena such as elevation. You can see here, I have showed you one previous image, or also on contour, DM, DTM, as I am saying in previous classes. So the contour lines which connects the equal elevation or equal data set point. So here you see there are 10 meter, 20 meter, 30 meter, 40 meter, 50 meter elevation from mean sea level. This is the topmost elevation. So spot elevation are the height between the contour lines are shown in as this point 58 meters. So you can see this is 58 meter. How this 50 meter, this 40-meter line, I hope I'm clear to you. This 50-meter elevation, same contour line, 40 meter, then 30 meter they made, then 20 meter of this equal point of 20 meter elevation, 10 meter elevation. Sorry, my pointer is not going appropriately, but I hope I may be clear to you. So this is called as contour lines. of equal elevation. I hope I'm clear to you. And when they are close together, contour lines show the steeper slope. See here, these are the steeper slope. It is very steep. This portion is steep, very nearer contour. And if you see here, these are the farther. This is okay. Slope is normal, not that steep. And when it is far apart, contour lines show the gentle slope. As I told, that is near it is showing the steeper slope. And this is called the contour interval. Between two contour, it's called the contour interval. So contour lines are the line that connects the location of equal value of raster data of equal elevation. Okay. So what is overlay? Generally, in advanced analysis, spatial analysis, overlay plays very important role to understand any Earth surface feature. As Sir has given the example for any data sets, when we are discriminating, uh, like a disease spread zone or any like uh, uh, like dangerous zone. Here, one is the vector of this polygon, and I will show through my pointer. One is the vector of this polygon, another is the lines and the vector of the danger zone. What we did, we overlapped this. So what we got this image, final image. Okay, so this is the overlaying. So overlaying operation can be addition, multiplication, comparison, subtraction, etc. can be performed on both raster and vector model in GIS. It can be on the vector data or it can be on the raster data also. Where overlay can be perform operation can be performed on both kind of data sets. See, as I showed in my first class itself, such kind of map where we are having the city boundaries, the streets, the vector. This is the polygons. These are the land uses rasters. These are the elevation raster, and finally we are getting the real world. So to overlay all these feature, we are getting the final real world map. So the overlay works for both vector datasets and raster dataset. For the both kind of datasets, you can see here it is working on both raster and vector data models. Okay, so don't get confused in overlay. It is the operation to understand the earth surface feature more clearly through different analysis of overlaying. So on the vector and raster datasets. So this is the class example. As I showed you, this is the class example, and this example I have taken from the Google, showing you the vector and raster data, how it works, the overlay operation to understand the real world feature more accurately. Okay, I hope I'm clear to you guys. Okay, now let's move further. This is the overlay analysis. Now, the cubic convolution, there is one question regarding the cubic convolution interpolation. It is the similar to bilinear interpolation. In bilinear interpolation, what we are having the nearby the cell, four cells. Okay, but in cubic interpolation, similar to the bilinear interpolation, in that we takes it takes the average of surrounding cell instead of four nearest cell. The output value is based on the averaging of 16 nearest cell. As sir has showed one figure also, here I am not having that figure. So I hope you may understand. There are 16 nearest cell which are averaging and giving you the interpolated value of the particular cell. So the cubic convolution works upon the 16 nearest cell. It is a bilinear interpolation. Okay. So until here, I am clear to you guys. If you have any queries, any question, you can come forward and ask me. Okay. So the last topic is the data limitation in uses in GIS. So as sir has discussed in the last lecture of this week is the ownership and the copyright limitation. Datasets having the ownership in GIS, in remote sensing datasets, different satellite data have been taken by different websites, and they are having the copyrights. Like it can be taken by the students or academician, or it can be taken by the researcher or any other industrialist or commercialist people. So it has some ownership to different website or different organization, and it has the copyright to give or provide this data to the public domain. And the data sharing policy, they are also having some policy until what resolution or until what temporal scale they can provide us, or not every latest data are open to the general public, because they have made some security and privacy policy also. Cost recovery and price, generally, as sir taught, sir has given the example of USA. In general, whatever data they are producing, they are utilizing in 100% manner. The cost, this cost recovery, they are getting 100% whatever they are putting. But in India, generally 16 to 70% cost recovery is taking place. Generally 40 to 30% data are getting not in use. So there is the limitation. And the public and private organization of geodata, so what are available for public, what are the available for private organization or a specific field of application purposes. The data security and regulation. So data security, like some data have been coded to the general team member or organization people. Some data is openly available, as I told you, the high resolution and recent published data. It can't be open for general public easily, so some authentication is needed. So they are having some privacy and policy of these kind of things. So these are the data limitation in remote sensing. So I hope I'm clear to you guys. I have completed this week lecture, all the problems. So please go through the assignment. I hope you are able to solve this assignment. If you get any doubt, you can, or any query, you can come, you can talk to me, and you can interact me on this my mail id. Thank you guys. The lecture will be available on this YouTube channel, and the slides I will share to the given the problem solving link. Okay. Okay, thank you guys. Thank you for patiently hearing me. I will provide you all the slides. Thank you.